The next step in neutrophil function will be destruction of the phagocytosed material. Destruction of the phagocytosed material. So the neutrophils will phagocytose, form a phagosome. The phagosome will join with the lysosome, and that's called a phagolysosome. And then the phagolysosome will then be the area in which the material that was consumed is destroyed. So that's what we're talking about now, destruction of phagocytosed material. The destruction of phagocytosed material can occur in two ways. Remember that there is an oxygen-dependent mechanism, which is actually the best mechanism of killing, and then there is an oxygen-independent mechanism. And so these are the two ways, and as I've already said, the oxygen-dependent mechanism is actually the most effective way by which killing occurs. Now, this requires a little bit of biochemistry to understand this mechanism, and because there's going to be a disease process that's important in this discussion, I do need to review some of that biochemistry with you. And I think the easiest way, again, would be for me to simply just create a whiteboard and explain this. So the mechanism by which a killing occurs is going to be oxygen dependent, so we're going to obviously start with oxygen. And one of the very first reactions that's going to occur is that oxygen is going to be converted to superoxide. All right, so superoxide. And the enzyme that does this is NADPH oxidase. So that's the first step. NADPH oxidase will take oxygen and convert it to superoxide. Very quickly, in an almost instantaneous reaction, superoxide will be taken by superoxide dismutase, which is an enzyme that we've already covered, and superoxide dismutase will convert this superoxide into hydrogen peroxide. And then hydrogen peroxide will be grabbed by myeloperoxidase and will be myeloperoxidase, MPO, and will be converted to bleach, which is basically HOCl. So, and HOCl is the key molecule that is then going to destroy the organism. This biochemistry is all high yield. You have to know each and every one of these reactions, and you need to understand the step-by-step generation of this final product because there are going to be diseases that are going to apply to these different chemical reactions. So with that as a background, now let's go back and read together. So in O2-dependent killing, which is the most effective mechanism, what's going to happen? HOCl, i.e. bleach, is going to be generated by the oxidative burst in the phagolysosome, and it's this HOCl that's going to play the key role in destroying the phagocytosed microbe. All right, next slide. Now, what's the mechanism? I've already gone through this, but let's read through it one more time. So oxygen is converted to superoxide by NADPH oxidase. That's also called the oxidative burst, by the way. Superoxide is quickly converted to hydrogen peroxide by superoxide dismutase, and then hydrogen peroxide is converted to HOCl, or bleach, by myeloperoxidase. So all of these are high yield, these enzymes are high yield, etc. Now, that's the normal, and there are a couple disease states in which this normal can be disrupted. And so the first of those is called chronic granulomatous disease. What happens in chronic granulomatous disease is that you get poor O2-dependent killing. Because O2-dependent killing is defective, the patient then gets chronic granulomas and gets regular infections and develops granulomas. So that's called chronic granulomatous disease. Now, where is the defect? The defect is due to NADPH oxidase. Now, this could be X-linked or autosomal recessive, but the key problem is that there is an NADPH oxidase defect. Now, because there's an NADPH oxidase defect, the patients are going to have problems generating bleach, and because they have problems generating bleach, they're going to get infections. What's important here, and we're not done yet because there's a very important high-yield principle, is that the patients get infections, and they form granulomas with those infections, but the key type of infection that they're going to get are with organisms that are catalase positive. All right, and there's a list of 5 organisms that are very high yield, but I'm going to just tell you what I think is the most high yield in a second. But I just first want to discuss this catalase positive idea because it does show up on examinations as well. So can we just go back to a whiteboard for a minute? And let me just go back to these reactions again. So you remember that oxygen is going to form into superoxide, and then superoxide is going to form into hydrogen peroxide, and then hydrogen peroxide is eventually going to form into bleach, right? and this was mediated by NADPH oxidase, and this was mediated by myeloperoxidase. Now, I just want to remind you that when you think about this reaction, what's really happening is that we're eventually generating hydrogen peroxide, and hydrogen peroxide is going to be converted to bleach. There are really two ways by which we can get hydrogen peroxide to convert it to bleach. One way would be to undergo this reaction that I've drawn here, where oxygen gets converted to superoxide, and superoxide produces hydrogen peroxide, and then this hydrogen peroxide becomes bleach. And that requires NADPH oxidase. Now let's say that there's a patient who is deficient in NADPH oxidase, right? So this pathway is knocked out. There actually is another way by which this hydrogen peroxide can be generated to form the bleach. And that is that most bacteria naturally produce a little bit of hydrogen peroxide. So that for the vast majority of bacteria, we could simply, if we're lacking NADPH oxidase, we could simply take the hydrogen peroxide from this bacteria, grab the hydrogen peroxide from the bacteria, and then produce bleach that way. And so patients who have chronic granulomatous disease really don't have a problem with most organisms, because most organisms are going to have have hydrogen peroxide, and that hydrogen peroxide can be converted to bleach. However, there are some bacteria that also produce catalase. And catalase destroys hydrogen peroxide. So that if a bacteria also produces catalase, this pathway now gets knocked out. And if this pathway gets knocked out, and this pathway is also knocked out, this can no longer be produced, and therefore bleach can no longer be produced. So that's why we only get infections with catalase-positive bacteria, because it's with those catalase-positive bacteria that we no longer have any source of hydrogen peroxide. So I hope that's clear, because that is actually very high yield. Now, in particular, there are 5 organisms that patients get infections with. Staph aureus, but everybody knows it, and it's a very, very classic bug, and it's not really the one that shows up on examinations most often. So Staph aureus is a catalase-positive bug, and it is a common bug that will arise in a patient with chronic granulomatous disease. But I would tell you, in my own opinion, more important is Pseudomonas cepaceae. So Pseudomonas cepaceae is actually another important bug that is catalase positive, and that can also result in infections. And because Staph aureus is almost known by every medical student, examiners like to go after Pseudomonas cepaceae. So do not forget Pseudomonas cepaceae in the context of chronic granulomatous disease. I hope that I made that clear. But anyway, all this stuff is high yield, and it's a lot of fun because we get to tie in biochemistry and microbiology with pathology, and that's really what medicine is all about. The next important principle concerning chronic granulomatous disease is something called the nitro-blue tetrazolium test, i.e. the NBT test. Now, this is a test that's used to screen for chronic granulomatous disease, and what it does is it asks the question, this test asks the question, do we have the ability to convert oxygen to superoxide? If oxygen can be converted to superoxide, the superoxide will actually change the NBT, or this nitro-blue tetrazolium, to blue. So why don't I make this super clear for you by drawing it in a picture. Again, you start with oxygen, and the oxygen gets converted to superoxide, as we've already stated, and then the superoxide gets converted to hydrogen peroxide, and hydrogen peroxide gets converted to HOCl. Right? Now, what does the nitro-blue tetrazolium test ask? It asks the question, is this reaction intact? And if this reaction is intact, if you introduce the nitro-blue tetrazolium into the test tube with the neutrophils, this will then turn blue. Okay? If the reaction is intact, the dye will turn blue. So if the reaction is not intact, the dye will actually remain colorless. Right? And so patients who have chronic granulomatous disease are not able to produce this reaction, and therefore they will not be able to change the dye to its blue color, and the dye will remain colorless. So that's an important test to be familiar with. Now, there is another disease that can also affect this pathway, and that is the fact that MPO converts. Remember that MPO converts hydrogen peroxide to HOCl. MPO can be defective as well. And if MPO is defective, that's called an MPO deficiency. And again, patients will not be able to produce bleach. So in MPO or myeloperoxidase deficiency, the interesting thing is that the vast majority of patients are actually asymptomatic. So in real life, if you were to ever see such a patient, which is very rare, but if you were to ever see such a patient, they would be asymptomatic most likely. However, on examinations, they get an increased risk for Candida infections. And I guess in real life as well, if they're ever going to have symptoms, it's going to be Candida infections, although usually these patients don't have symptoms. But on board exams, they usually have an increased risk for Candida infections. I'm going to talk about this in a slide in a minute. However, what I want to highlight here, since I took all the pain to draw this picture, is that the NBT test will be normal. Because in these patients, in myeloperoxidase deficiency, this reaction is fine. The problem is this reaction down here. So the NBT test will turn blue, but the patients will be lacking myeloperoxidase instead. Okay, so with that, let's actually talk briefly about this slide, which is the next slide, which is the MPO deficiency. So MPO deficiency results in what? It's a defective conversion of H2O2 to HOCl. I've already explained that to you. And most patients are asymptomatic. However, if there ever is a problem, the problem is usually an increased risk for Candida infections. And high yield NBT test is normal. So it is important to be familiar with myeloperoxidase deficiency. Now let's go forward. The second way by which neutrophils can kill is called O2-independent killing. It's less effective, and it occurs via enzymes that are present within the leukocyte, usually within the secondary granules of the leukocyte. So for example, lysozyme is an enzyme that's useful for destroying microbes. Major basic protein, this is major basic protein here. It is an enzyme present in eosinophils, which is useful for destroying microbes as well. And this is a little less effective than oxygen-dependent killing. The final stage of neutrophil arrival is called resolution. And so once the infection is destroyed, within 24 hours, the neutrophils will disappear. Now, it's important for you to know for examinations, they like you to know how neutrophils disappear. And what happens is the neutrophils die within the tissue, and they die via apoptosis. So all neutrophils, once they get into tissue, will die within the tissue, and they'll die via apoptosis. And recall that pus is basically dead neutrophils within fluid. And that's the sort of the final resolution, which is you have to know that it's very high yield. Neutrophils undergo apoptosis, and that's the way by which they resolve themselves within the tissue. Now, once the neutrophils are done their job, the next phase will be to bring in the macrophages. Can you remember I told you that there were 3 phases of acute inflammation? There's a fluid phase, which occurs immediately. There's a neutrophil phase, which peaks at 24 hours or a day into inflammation. And then there's a final phase, and that final phase is the macrophage phase. And so this is now what we want to briefly touch on, the macrophage phase. And so the macrophages peak 2 to 3 days after inflammation begins. They occur after the neutrophils arrive, and they're derived from monocytes in the blood. So you've got these monocytes floating around in the blood, and it's the monocytes that eventually get into tissue, and when they get into tissue, we call them macrophages. Now, we should just be thankful that the macrophages, i.e. the monocytes, they come into the tissue the exact same way that the neutrophils do. So they use margination, they use rolling, they use adhesion, they use transmigration. So guess what? That makes our life really easy, because now we don't have to repeat all of these steps. We're already familiar with them. Once the macrophages get into the tissue, they actually ingest via phagocytosis, and then they destroy the phagocytosed material using enzymes in the secondary granules. For the most part, macrophages don't really do a lot of oxygen-dependent killing. Their primary mechanism is oxygen independent, using enzymes in the secondary granules, and I would say one of the key enzymes is lysozyme. So we should be familiar with the fact that lysozyme in the secondary granules are very useful for the macrophages to destroy phagocytosed material, or to kill off phagocytosed material. The final point to close off this section is that the macrophages, in my mind, it's sort of the way I think about macrophages, is that they are managers. They then manage the next step of the acute inflammatory process. And so when the macrophages come in, they sort of look around, they're managers, and they say, has a good job been done? Does something more need to be done? Do we need to call in somebody else? So if they come into the tissue and they see that Well, excellent job. The neutrophils have really killed off everything, and it's now time to begin the next step. They will then induce resolution and healing. So they'll kind of look around and say, okay, these bugs are dead, these bugs are dead, these bugs are dead. Neutrophils did a great job. Let's call in healing, because it's now time to fix the tissue. And the way by which they do that is partially by secreting IL-10 and TGF-beta. Now, the key thing about IL-10 and TGF-beta, these are both things that shut down the inflammatory process. So I think it's important to remember that IL-10 and TGF-beta, they're kind of anti-inflammatory. They sort of shut down the inflammatory process, and then they also allow for the eventual calling in of healing. And we're going to talk about wound healing a little later in this chapter. Another possibility is that the neutrophils can come in and they could say, uh-oh, we got to do a lot more work. They may come in 2 to 3 days later and say, neutrophils look like they need some help. So they can actually call in additional neutrophils, allowing for continued acute inflammation. A couple important points here, which become high yield for examinations. IL-8 is the mechanism by which the neutrophils call in, is the mechanism by which the macrophages call in the neutrophils. Again, I'm going to repeat this because it's high yield. IL-8 is the cytokine produced by macrophages that call in the neutrophil. Now, when additional neutrophils are called in, that's going to result in continued acute inflammation. So although we call it acute inflammation, and although it peaks at one day, acute inflammation is not defined by time, it's defined by the response. So for example, a patient could undergo acute inflammation and have acute inflammation for 6 weeks. And that's because the macrophages keep secreting IL-8, which calls in more and more neutrophils. So the hallmarks of neutrophilic inflammation, particularly the formation of pus, tells you that there is a continued acute inflammatory response. So please be aware of that, because sometimes examiners like to confuse you by saying that there is a process that's been going on for 8 weeks, but the patient's still coughing up pus, and so what is actually happening, and the notion here is that it is still an example of acute inflammation, even if it's 8 weeks into the infection, because of the fact that you still have a neutrophilic response, and neutrophils are what define acute inflammation. Now, another possibility is that the macrophages can come in and they could basically sense that the organism is a particular type of organism that needs to be walled off to protect the rest of the host, the organ. And so they can actually result in, they can actually call in or create an abscess. And what's an abscess? An abscess is an area of fibrosis. So let's pretend that this is an organ. This is an organ. And so what the macrophages can do is they can create a wall of fibrosis around the area of infection, and so that the inflammation sort of gets trapped within this space. And that would be called an abscess. An abscess is basically a walled-off area of acute inflammation. And the neutrophils are really the ones that manage the formation of an abscess, and they would form an abscess in response to very particular organisms, as you're well aware of. And then finally, the last thing that the neutrophils could do, they could come in and they could say, uh-oh, looks like the neutrophils aren't able to handle this. For example, this is virus, and virus is not well handled by the neutrophils. And so the macrophages could call in chronic inflammation. They ingest some of the antigen and the microbes, and then they express it on their MHC class II because they're antigen-presenting cells. And it's the expression of those particles in MHC class II that could eventually result in the activation via helper T cells of chronic inflammation. And so again, macrophages are managers of the acute inflammatory process, and they can then dictate what's going to happen next. And so with that, we're going to be here concluding acute inflammation, and our next section is going to be chronic inflammation, but let's stop here and give you a chance to take a little bit of a breather.